Our next presentation is Tim Evans with Cisco, presenting on monitoring BGP using open source OpenBMP and Apache Kafka.
Hi, great, thanks. So yeah, I'm going to talk about monitoring BGP and Route-Leaks using OpenBMP and Apache Kafka. So the first challenge is to collect the BGP data, and traditionally to collect the BGP data, we could use VTY access. The problem with VTY is that it is not real-time, it's poll-based. You have to make requests to the router and issue commands in order to get the data. Typically, the requests that you do to the router with the show commands are large output responses, so the results can be in 100+ megs of data, which can impact the router's management plane, so it's not typically desirable. It can also be slow because you have to make requests to the router, but in addition to that, the router processes a request in a synchronous fashion, so it doesn't do it in asynchronous. So you have to do a request, make the wait for the response, and then issue another request, wait for the response, to which can cause a backlog. If you're planning to access all your routers, it ends up becoming slow. Because of the access requirements for making the connection, it typically also adds to the slow connection time, as well as requires the management system that wants to collect the data to maintain credentials, as well as the inventory information for the devices that it's going to connect to. So it becomes harder to maintain the inventory database in order to even collect the data to begin with. And the maintainability is pretty complex because even with the BGP, or even with the output from the data, it can vary by platform and version. And when it varies, even if you had Yang or you had other data representations of the information, it still is going to be revision-based. So you still find yourselves having to maintain some type of cache for this router, this platform has this capability. And you have to end up maintaining that and updating it every once in a while. So another method to collect the BGP data is to use packet capture. And if you packet capture, you will get the pre-rib information. You'll get all the information for the BGP peers, and you'll get the BGP updates as they are. But it doesn't really work over encrypted transports, and it doesn't work unless you have a specific architecture to support the packet capturing. So if it's multi-hop or iBGP and the session traverses multiple interfaces, the collector has to reassemble those potentially multiple packet capturing feeds in order to determine if determine where the packets, the sequence of the data. And potentially it could have to do reassembly as well, which makes the collector more complex and harder to implement. Even with the packet capture, the collector doesn't know what the router is doing with the peering, so it doesn't have any visibility to the states of the peer. It doesn't know what the peer is doing as far as post-policy and pre-policy. So it can only make assumptions, and because of that, the packet capture typically requires that the collector has to parse the open messages and has to maintain the monitoring of the BGP keep alives, which is just more work for the collector and makes it kind of a burden. And it can also be a security concern because the fact that you're packet capturing, it can be a problem if you're doing this in a live, always on, always monitoring fashion. And you might have to audit that in order to make sure that you're not capturing data that you're not supposed to be capturing to begin with. So it just makes it a little bit more difficult. BGP peering is probably the most popular way to monitor BGP, but when you monitor via BGP peers, you are only going to get the interpreted view of the information, which means you're only going to get what the router tells you. And that means the router has to process the updates. The router has to understand the attributes and has to accept the updates in order to send those to you. So even if you tried to do pre-policy with add path, you would still be limited to what the router has decided that is valid. So if anything was attributes unknown that may or may not be sent to you, as well as next hop, AS path loop, or any other invalid criteria that would cause that update to not even be considered, you won't see it. So you don't really get a true representation of what the router is actually seeing, especially if you're going to try to do move the control plane out of the router, at least from the BGP perspective. You really need to see what the router sees 100% in order to do that. So with BGP peering, you also do not have the visibility of the peers. You have absolutely no idea what address families or capabilities have been exchanged on those peers. You don't have the details as far as if there's address families that are being conveyed to which your peering session does not have configured. So you only see, once again, what the router tells you. You could try to do pre-policy, which some people do with peering with all the other peers. But then that becomes a situation of just how often do you, or how far can you go with peering with everybody else just for monitoring perspective. So it becomes a scalability issue. Standard peering can be a security concern because it is inline. It's implementing the BGP stack. So when you peer with the router, you're peering with the same stack, the same code that's used for the production forwarding of traffic and working with BGP, which if your collector is super robust and really great and trusted, then that might be fine. But if you're using and trying out different collectors and different tools, it may be of a concern to turn on monitoring on your core route reflectors or your edge peering routers, your PE routers. So it's problematic in the sense that you do jeopardize potentially the BGP stack. And the same thing for an inbound policy. Even though you don't expect to receive anything from the peering, you may actually still receive something, and the BGP stack still may implement parsing of that update, to which still could cause a problem. So an answer to this is to use BGP monitoring protocol, which is implemented in Cisco as well as Juniper today, as well as I heard Go BGP as also implements it. And what it is a way to establish a monitoring session from the router to a collector. And you can have several collectors out there, but in general, you have typically one TCP connection that is established to the router and the collector, and through that persistent TCP connection, you get all of the peer information, which is an encapsulated BGP update or notification or open message in BMP. So you get that information as the router receives the information, you get that information to the collector. So one stream can handle hundreds of peers. And the configuration is very, very easy to configure that. So unlike having to configure all these peering sessions, from monitoring perspective, you configure just that monitoring server, and you just toggle on or off monitoring on a per-peer basis or globally. And it's implemented very efficiently within the router because once the peering session has been established, you have enough information for the BMP headers to reuse that for the life of that peer. So what that means is that the router can just attach, basically, or append the BGP update, send the message through BMP without having to parse the BGP update or do anything with it. It is implementation specific, but in general, it doesn't have to do that. So it's very fast to forward the BGP data. Because it's BGP data, it supports every address family. So link state, VPN, v4, v6, unicast, everything is supported. Every attribute is supported. And even if it's brand new and it's something that the router doesn't even know what to do with it, it's technically still supported because as long as we get the information and forward it, we can parse it or interpret it and use it from the collector side. So everything is supported. When the connection is established to the BMP router, the router will do a rib dump, and it will dump the information from the peers, which allows the collector to synchronize itself with the current state. And once that's done, it doesn't need to do a rib dump anymore because it's a persistent connection. It's always maintained, so it's just incremental updates from then on. So if your peers are several weeks connected and the BMP session is several weeks connected, then it was only one rib dump that took place. If you wanted to do a rib dump, you could do a rib dump just by doing a route refresh. And that would cause those updates to be flooded in again and therefore directed to the collector, and the collector would get a copy of it. The draft is in currently revision 15, and it's in its final stage. So it should be hopefully approved soon. So OpenBMP is a collector of BMP messages from the router. It maintains and establishes the connection to the router to maintain that connection. And it's open source. And when it maintains that connection with the router, it will take that data feed and send that data feed to Apache Kafka, which is a message bus that performs extremely well in terms of speed. It handles hundreds of thousands of messages per second with very little memory, so it's very fast. And from there, you can then have any number of consumers. So kind of like with multicast, where you have senders and receivers, and you join a group, the sender does not need to know about the consumers or the receivers. It basically just sends messages, even if nobody's there. It doesn't care. It just sends the messages out there, which is going to Kafka. And then if there is a consumer, great, they consume the messages. If there's no consumers, no harm, it doesn't care. What this allows us to do with this is to create a large number of consuming applications, and they can be use case specific. So you can create what you need in order to get from this BGP data, which may not be a huge amount of data collection. It may just be that you're looking for specific prefixes that have a community string. We provide a MySQL consumer that's open source. And the MySQL consumer will take all the parse messages and it will put it into the database. It'll maintain state, so you can look at the RIB information on any one of the peers, on any router, and you can see what the active pre-RIB information is for that and post-RIB if post-RIB is being sent. And it also maintains a history. So every time the prefix changes, as far as attributes change, there is a log entry that you can go back and then correlate that back together to draw the topology for a point-in-time representation. The file consumer is another consumer that we have out there that implements the parse messages, but it mainly is for you just to look at it from the parse message view. But it does do the binary raw messages as well. So in addition to the parse messages, we do send the binary data, and that binary data is exactly what was sent by the router. So with that, there are three primary use cases for collecting the binary data. One of them is to do long-term archival. Storing this data is extremely efficient to store it in the binary raw format because a full internet RIB dump is only 12 megs, so it's not that much. The same exact data in a concise parsed format is 100 megs. And if you put that into other formats like JSON or XML, it becomes almost 500 to even greater size. So very good storage to use the raw format. One of the other use cases is to support other applications that want to interact natively with BMP. So instead of establishing another BMP feed from the router to another application, that application can use the same Kafka feed and use the binary stream, and it can take that data and consume it natively. So other third-party applications, anything that natively speaks BMP can use that stream. One of the other use cases is that if you need to do BGP structure analysis, where you want to look at the order of the attributes or how efficient the packing is being done in BGP, or if you want to look at all the malformed updates or anything that the router ends up rejecting, you can do analysis at the BGP level with the binary stream as well. So we have multiple consumers. We also have Elasticsearch. We have ODL. We're working on MRT consumer as well that will produce the MRT dumps on an interval. And we're working on a BMP connector that will also connect other BMP servers transparently to this framework to do this. So OpenBMP.org is where you can go to get more detail, as well as GitHub. Everything is under GitHub/OpenBMP. So more detail on Apache Kafka is, unlike other message buses, this is kind of like a cache, and it's a log, and it's in a window of time. So you can establish, based off of configuration, how much cache or log you want to maintain. Typically, we recommend 36 hours. You don't really want to go usually longer than that, but 36 hours means that a consuming application that wants to consume data can go as far back as 36 hours into the stream, and then it can catch up. So it can read the messages at as fast as a rate as it can read, and catch up to where the messages are being produced. So there's a smallest in and there's a largest in. The largest is where the messages are being produced, and the smallest is the oldest message that's available, which would be like 36 hours ago. An example of this would be if you have 3 different consumers that are running, and one of them, let's say it's MySQL, and let's say you want to do a schema change, and you want to stop the MySQL consumer, and you want to apply the change to the schema, well, with this environment, you don't have to actually disable any other consumers. They can continue where they are, and they can continue to run with the real-time data. You can stop MySQL, and let's say you stop it at sequence or offset 6. You can then basically do your work, restart the MySQL consumer, and it will resume at offset 7. So it doesn't miss any of the updates, and it doesn't require rib dumps to be resent just because the consumer restarts. So slow consumers also work like this. And slow consumers would be consuming applications that you write really fast. Like if you want to analyze something because you had an incident and you wanted to write a Python script really fast to consume the data and just check things out, your application may not be efficient. And if it's not efficient, it may run slow. But that will have no effect at all on any of the other consumers. So they do have that autonomy. And you can load balance consumers. So this framework is more than just a JSON output of data. Or XML output of data that you get with a stream. This is a framework that supports consuming applications to scale. So you can scale your applications how you need to scale them to consume the messages. And OpenBMP ensures that the messages are put in order. So when you get an update and a withdrawal, you don't have to match the timestamps. Your order will be maintained on a per partition basis. So when you load balance, your consumers should be able to load balance correctly and process the messages in sequence as they were generated. So the architecture of OpenBMP is to establish a reliable collection feed of BGP data. So you can have one or more OpenBMP collectors, but you can also have BMP collectors or OpenBMP collectors for different groups. So if you have a backbone group and you have a cloud services group, and different people manage different routers, and you don't want somebody to touch your router, and you don't want them to be rebooting this box whenever they want to reboot it or do something that they're doing with it. So you can control that with your own collector, feed it into the same Apache Kafka bus, and you can maintain the stability within that environment with the collector going to Apache Kafka. And the collector has evolved over time. We have made it so that it lessens the burden on the router as much as possible. So the idea is to not require the router to buffer, not to require the router to do any extra work than it has to do. So it will forward messages regardless and send messages to Kafka even if the consumers are not there or not functioning. The consumers, because there's like a demarcation between Apache Kafka and the consumer layer, you don't have to worry about badly written applications causing a problem to your data feed, and it won't affect any other consumers. So applications at the integration layer within Kafka can crash all day long, and it doesn't have a problem at all. So you get a stable environment. If you don't want to develop anything, you can use one of the existing consumers, and you can integrate natively. Like you can use Kibana, and you can visualize the live data as it's coming in. And you can design dashboards and use that tool using Elasticsearch and the Elasticsearch consumer. So the message feed looks like this. And this is using just a standard Kafka console consumer, which is provided when you download Kafka. You can run this consumer. And in fact, you can use this exact same syntax. Of course, you change the host name. With this data, it sends basically the stream. And we went back and forth between using JSON or other structured format for this. And we decided not to because the data stream is more efficient when it's just the raw data that we're trying to send as compact as we can with it. So having to put descriptions to the fields and sending it in JSON or something like that, or if we try to use Yang or whatever, it would end up producing 500 plus megs worth of data when this is far more efficient and it's not that much. You can take any software package that can take in comma delimited or tab delimited fields and import this data. You can actually cut and paste this data right into Excel, and it automatically loads in Excel. You can use Excel's data drivers to load this dynamically, and it pulls it in. You can pipe this to awk, and awk will parse this on command line real time, and it's super easy to develop against. So to do some analysis, one of the things that we analyze a lot with this data is we analyze the AS path. And we need to maintain the order within the AS path. So traditional indexing, so if you, like an Elasticsearch with a string-based, text-based indexer or analyzer, or in MySQL, you have the text search engine. They analyze based off of words, and they don't really maintain the order, so it doesn't really help us when we want to extract immediately to the left or to the right ASNs, when we want to look at what's upstream or what's downstream on a prefix at any point within the AS path. So this is the method that we have been using for, we use it in code, in memory, as well as in the database, and it works universally between the both. And the way we do it is we basically iterate through this AS path, and we look at it distinctly, so we don't care if there's any prepends. And with that, we then record in a table or a hash table, we record the ASN that we're iterating on, and then the AS to the left and to the right. So in this example, if I wanted to look at 13355 and I wanted to say what upstream ASNs or providers does 13355 use, we can see immediately it's 1299 in this particular case. But if you expand this across millions of prefixes that we end up getting in, we get a distinct list of upstream providers as well as downstream. So we can tell if they're transit, not transit. We can tell if they are transit for anybody else, or are they just transit for themselves, meaning that these 10310 and 33612 are just behind them and not past. So with that, we use that heavily for the route leak monitoring. And in the context of this discussion, the route leak is defined basically as anything wrongfully advertised. So that can impact any number of prefixes. It's not just one prefix or 1,000 prefixes or whatever. It could be any number. It could be any address family. We're not limiting ourselves or restricting ourselves just to unicast v4 or v6. We want to expand and support theoretically any reachability information. We also, it's not just on what is being originated as far as originating ASN. It could also be that there was no path change at all. So in the case of policies being incorrectly applied, if you had no export that was there before, but now it's gone, technically you leaked that prefix that may have not been meant to be leaked, even though the AS path didn't change where you're monitoring. So normally, there's tactics for trying to prevent this so that you don't need to do this level of monitoring, but those tactics typically start to fall short, specifically around policy chaining when they get too complex and they start to overlap or conflict with each other. Mistakes are made, both with automation as well as with human mistakes. And one of the issues with the RRs or RPKI is that it traditionally focuses on public addressing, and it also is administrative, so it makes it a little bit harder to adopt immediately and theoretically maintain. So kind of using the 80-20 rule of monitoring for prefixes, we could look at hundreds of possible ways to do leak monitoring. But we also, if we try to narrow this down to say what is a general way to look at the route leaks, there's a few techniques that we can do to quickly identify potential route leaks without having this administrative database. So we can still include the IIR as well as the RPKI information, but we don't have to rely on it. So one of them is to look at more specifics being observed. So in this particular case, we already normalize our database. We already know with those rib dumps what we've received, so we know if we have a new prefix or not. So we can immediately check, and we can check to see if this is a prefix that's already known, or is it really truly a new specific prefix. If it's a new prefix, then we check to see if the originating ASN is the same or not for the aggregate. So we look up the aggregate and we determine, do those match or not? And if they match, then chances are this one's probably okay, because at least the originating ASN is the same as this new specific that's coming in. We still have other checks that we'll do on it, but if they're the same, we'll let it slide through at this point. If the ASN is not, so the aggregate is a different AS than the more specific, then we'd want to look at the upstream list. So we look at the upstream of the ASN, or the aggregate ASN, and we would say, what upstream providers do they have? And we would check to see if this more specific is within that list. And if that specific is within the same list of upstream providers, we would consider that as a most likely okay as well. Or if it's not in the list, we would send an alert and say that this is a potential problem. To give an example, if you run this query across all of the internet information, at least with the data feeds that we have, there are 8,000 prefixes right now that, or give or take, right now that basically would alarm under this condition. They are advertised in aggregates with specifics that do not match the same ASN, and the upstreams don't match. They are completely different upstream lists. So another check is to do ASN inconsistent checks. So that's specifically checking to see if there's more than one prefix, the same prefix is being advertised by more than one AS actively. And this is kind of period-based. So we do have a period of time because we do expect that there could be convergence, and there also could be cases where you are, like within Cisco, we have a lot of ASs, and we can move things around. And it could be that I get an AS from somebody, and they're like, cool, or a prefix, and then I want to move it to a different AS, and I'm going to advertise it. But chances are I'm not going to do it within a split second of time. It's usually going to be that it's a longer period of time that takes place. So we typically want to look at a period-based to see if this prefix is being advertised actively. And since we have the pre-rib information, we can see if the prefix is being filtered, and it may not be in your routing tables, but we can see that it's still being received, so we can still see that there's a conflict. And if there is a conflict, we do check the upstreams again. So we determine that do they share the same upstreams. And if they don't share the same upstream providers, then we would immediately alert. If they do share the same upstream provider, we'd want to check to see if it's equal or better in the sense of the advertisement. So based off of what we know as far as the standard selection process, but as well as the communities that we know that are being implemented, we can determine if that prefix is a threat. If that prefix is a threat to take over potentially traffic, we would want to alert. If it's not, we may not want to alert on that at this phase. If we were to look at this right now, there's roughly around 1,000 prefixes that actually match this condition today. So another check is to look for upstreams that change. So this, the best use case for this would be like if you have a public peering and your public peer that you're peering with decides to originate your prefix. So you advertise them your prefix, they in turn advertise it. They become an upstream for you, and in this check here, we specifically look to see if there's a new upstream. And if we suddenly see that this new upstream appears, we would alert and say that something's suspicious about that because that upstream wasn't there before. We also can do a level of monitoring at the same type of check is that if somebody was never a transit to begin with and they suddenly become transit, we can immediately alert on that as well. So that's kind of the same type of upstream check. Another check that we want to do is anything that's selection-based attribute changing. So any well-known communities that change, any communities within the topology. So with this collection process, we can monitor internal IBGP stuff as well as outside eBGP peering connections from the outside in versus inside out. And with the internal information, we can look at the communities, and knowing the community mapping, we can determine if there's anything that would be a selection-based change type of event. And if we see that, that could be something that we'd want to analyze on the spread of that change. One of them would be to look at geocoding as far as, is there a big regional change? Did it affect an entire region, and did something move between regions? And is there a conflict with region-based community identification? Or is there a change from customer prefixes that suddenly shifted over to a partner or suddenly shifted over to a public peer classification based off of community? And if that happened, we would want to be alerted on something like that if it impacted several prefixes or impacted a significant amount of distinct ASNs, originating ASNs. We can do standard snapshotting, so you can snapshot at any time the routing tables with all the attributes, and then you can do a very simple diff, and it can tell you if there's any significant changes with that. Same thing for scheduled reporting. You can do this interval-based. You can take snapshots every once in a while and alert if there's a problem with that. And any attribute can be monitored, so whatever you want to monitor within the attributes, they're available to look at them and to alert if there's a presence of an attribute or a lack of presence of an attribute, or if there's a combination that doesn't make sense. Like if you expect a certain community string to always have prepending, and let's say the prepending's not there. Or if you see that two community strings should never be on the same advertisement, you can alert on those types of conditions very easily. So another check is to look holistically across the entire data set. Using the same ASN analysis, we can look at the advertisements on a per AS basis with distinct prefixes. So we can count, for each ASN within the AS path, we can count the prefixes distinctly that we see that contain that ASN. So in this case here, the 3491 or BTN, we can see that we had 27,000 active prefixes that were being used distinctly, and it drops. And if it drops, we would then do a spread analysis on that and investigate how big of an impact that was. And if it was small or focused on a specific ASN or community, we might attribute that to traffic shifting and not consider it a problem. But if the spread was hundreds of ASs, that might be something a little odd or suspicious, and we might want to alert on that. And this is done in both a drop as well as an increase. We can also do the same thing when we look at the transit or the origination as well. So we can look at if a customer or a public peer or anybody from the origination perspective, we can see if they suddenly increase or decrease within origination. And we can alert on that. Now, this is different than peer statistics. We also do have peer statistics with BMP, so you can see exactly how many prefixes have been accepted with pre-policy and post-policy. You can also see how many prefixes have been rejected or duplicate and so forth. With that data, that's not on a per ASN basis, that's the whole entire peer, but we would also alert on something like that as well if the peer were to change in a significant direction of positive or negative. So no matter what type of analytics that you want to do, OpenBMP does collect the data and make it available in a way that you can provide a stable environment for the BMP collection of the data and then have that somewhat volatile environment for consuming applications, which is totally fine. You can satisfy different types of analytics, so real-time, on-demand, discovery, investigation, topologies, pretty much anything BGP related you can feed through and analyze within using OpenBMP. And you can use this today. So we do have a Docker Hub install. You can actually do Docker pull OpenBMP/AIO, which stands for all-in-one. It includes everything configured, and you can start playing around with it. Juniper and Cisco does support this, so you can turn this on lab routers or anything else. We also can make available live feeds to where you can start playing around with this as well from any internet connection. And all the documentation is on openbmp.org to do this. So with that, does anybody have any questions? Great. Okay, got some time back.
Job Snyders, NTT.
Oh.
Tim, thank you so much for pushing OpenBMP into the open source world. I will dare to go as far as say that this is a really sexy piece of software, and I see many, many opportunities to leverage the architecture you built to, for instance, increase the quality of our prefix filters, reduce the size of those, quicker find route leaks, as you demonstrated. So thank you very much. However, maybe your employer might need to do some extra work on feeding stuff into OpenBMP. Because one of the, if it were to work stably on iOS XR, I would deploy it tomorrow. But there are route leaks and route refreshes in some scenarios, and I'm lacking the post-policy bits. It only sends pre-policy, for instance, so I cannot analyze real-time whether the router is honoring the routing policy. So how can we help you make this happen? Because you finished this.
Yeah.
You got spare time now.
Yeah. So, obviously, I think one of the challenges with BMP is it's been around for a few years, And I think the collection hasn't been mature enough, and it hasn't really been adopted too well. So it's been implemented, but as you mentioned, the implementation is pre-policy only right now on Cisco, and it does use route refreshes as a way to collect the data, which has its advantages and also negatives. But within that, I think that how everybody can help is obviously vendors typically respond quite well to customer demand and customer requests. I really believe that everybody will find that this is really useful, and it's a very efficient way to get this data in a live fashion. This isn't interval-based or anything. It's live going into the data stream. So I think it's always good to do that. But I hope that I do have some influence. So we are going to also be, we're right in the middle of discussing changes to support like the post-policy information, as well as not having the route refreshes being a requirement to do the conveyance.
And the memory leaks.
Yeah, and the memory thing is, that will go away as well, because we will start using, it won't be, because that's done because of the route refreshes, right? The route refreshes come in, it's got to take in all this data, and then it doesn't store it. So it needs to, it either has to drop it or cache it, which is why it does that right now. That will change to where it'll be more maintained, which is pretty much what you see on the Juniper side, which is what Juniper's doing today.
Sounds good. Thank you.
Thanks. And I would also ask everybody to also ask other vendors to start implementing BMP, so even like Alcatel and everybody else to get BMP implemented in other products. So,
Randy Bush,
yes.
IJ, and other strange places. You said you're offering feeds?
We're not offering our data feed, so we get a data feed from you. We don't make that available.
I was just wondering how you decide privacy and policy issues relaying feeds.
We don't give out anything other than our own feed that we have, which is only to ourselves, so the Cisco Sciences Network. So that's the only one we...
Thank you.
Yeah.
Tony Tauber, Comcast. So is the example thing that you have, the Docker, does that include, what pieces does that include?
The Docker image?
Yeah.
The Docker image includes Apache Kafka. It includes OpenBMP collector. It includes the REST interface to the MySQL database, and it also includes MySQL or MariaDB. And it's kind of like an all-in-one package so that you can play around with all of those. We'll be bundling also the other stuff as well, like Elasticsearch, things like that, so that you can also play with Elasticsearch if that's how you want to visualize the data. It's meant primarily for you to test it and evaluate it and play around with it without having to do much work at all. In fact, you should, in theory, be able to just do Docker pull, install it, and do Docker run, and you should be immediately working with it that fast. So it includes everything to get started with it.
Okay, but it's not necessarily intended to be performance tuned or whatever.
When you run Docker, you specify the memory constraints for the Docker container. That would be the only constraints. And it is disk intensive to some extent. So depending on the retention of how long you want the data for, that could require some disk space. But that would be the only constraints. It can run on a 4 gig machine fine or more, depending on how much peering or how much information you want to put in there.
And is there like a community discussion list? I looked quickly at the webpage, but I didn't see
Say that again, I'm sorry.
Is there like a discussion list or a mailing list for?
We don't have a mailing list right now, but you can always go into GitHub, register any questions or anything there, but then also we could create a mailing list for that.
Maybe. Okay, thanks.
Yep. Okay. Great, thanks.